Morning Year 12, I'm going to do a video through work example 7.1 from the textbook. Let me read it out for you before we get started. Potassium hydrogen phthalate, also known as KHP. Remember we did the making a primary standard from it. There's its formula. It's a good primary standard for standardizing alkali solutions because it's an acid. It contains 1 acidic hydrogen per formula unit. Potassium hydrogen phthalate, 0.917 grams, was dissolved in water and titrated with approximately 0.2 moles per litre sodium hydroxide solution. 27.2 ml of sodium hydroxide solution was needed to reach the endpoint. Calculate the accurate molarity of the sodium hydroxide solution. Where do we start? Formula. Let's put up KHP. KHC8H4O4. That's the phthalate. And we're reacting it, so that's our acid. And we're reacting it with our base. Oh, states aqueous. I'm going to do a solid arrow because acid plus base is very spontaneous. It will go to near completion. What do we got? Well, the hydrogen from the acid will go over to the hydroxide and form water. Acid plus base gives water plus salt. What salt have we got left? Well, hydroxide's reacted away. We're going to have the sodium and the conjugate base of the KHP. So KC8H4O4, negative would be the conjugate base, but I'm going to put the sodium with it too to make a neutral species. Aqueous, that would be soluble because it's attached to a sodium. Is it balanced? Well, it was monoprotic, we formed one mortar. Yep, we're all good. Okay, let's look what info they've given us in the question. Okay. So we've got a mass of KHP, 0.917 grams. Was dissolved in water and titrated with approximately, calculate the accurate, okay. All right, so we know we've got our mass of KHP, so we can work out our moles of KHP. So it's going to equal our mass divided by our molar mass. Let's get our periodic tables and start adding up this molar mass. Potassium is 39.10 plus our hydrogen. Well, we've got 1, 2, 3, 4, 5. 5 times 1.008 plus 8 carbons. 8 times 12.01 plus, what have we got left? Oxygens. The 4 oxygen. 4 times 16.00 grams per mole. I did bring my calculator in. All right, let me put it in. 0.917 divided by 39.1 plus 5 times 1.008 plus 8 times 12.01 for the carbons plus 4 times 16. Okay, so I get 4.49 times 10 to the negative 3 moles of KHP. So that means our moles of sodium hydroxide at equivalence. Let's determine that. Moles of sodium hydroxide at equivalence is going to equal the 4.49 times 10 to the negative 3 moles of KHP multiplied by the ratio between the two. That's a 1-to-1. 1 mole KHP to 1 mole sodium hydroxide. Notice the fractions this way around, so that the KHP moles up the top cancels with the KHP moles down the bottom, okay? Now it didn't matter because it's 1-to-1 here, but don't make that mistake when it's 2 to 7. And you go, oh, is it 2 to 7 or 7 to 2? Do it right all the time. Okay, so at equivalence, we must have the same number of moles of sodium hydroxide. Okay, now in the question, it tells us the volume of the sodium hydroxide, and it tells us that that is in 27.2 milliliters. Okay, so the volume sodium hydroxide equals 27.2 milliliters. Why am I working all in red? Doesn't matter. So our concentration of our sodium hydroxide equals the number of moles, 4.49 times 10 to the negative 3 moles, divided by the volume in litres, because moles per litre, 0.0272 litres. Let's put it in my calculator. Divided by 0.0272, and I get the answer to be 0.16508 blah blah moles per litre. Significant figures, let's go back. Our inputs are 3 significant figures for the mass, 3 significant figures for the volume, so we can report this to 3 significant figures. So, there's the first, there's the second, there's the third. The fourth is a 0, so we don't need to round up. So it's 0.165 moles per litre to 3 sig figs. I'm going to check the answer. Hopefully it's not out. 0.165, that's what they got. All right. I'm going to attempt question 2. Let me rub this one out. Eraser. All right. So worked example 7.2 on page 199. Let me read it. The acidity of a particular white wine was determined by titrating 25.0 milliliters of the wine with 0.0511 mole per litre sodium hydroxide solution. 8.70 mil of the sodium hydroxide was required. Calculate the molarity of hydrogen ions in the wine. Assume that the hydrogen ions came entirely from the diprotic tartaric acid, given the formula there, H2C4H4O6, and calculate the concentration of tartaric acid in the wine in grams per 100 milliliters. Okay, where are we going to start? Balance chemical equation. It's given us the tartaric acid there. Should know sodium hydroxide. All right, so the tartaric acid, H2C4H4O6. Notice that they've repeated the H's there. They've distinguished that these two are the hydrogens that will come away. So this will always stay together. Plus our sodium hydroxide, aqueous. What are we going to get? Well, it's diprotic. So we're going to need, for 2 hydrogen, H pluses, we're going to need 2 hydroxides. So I'm going to start that way. And that's going to form 2 waters. Okay, what do we got left? The conjugate base of the tartaric acid will be that minus the 2 hydrogens. Let's write it up separately for this one. C4H4O6, because it's lost 2 H pluses, it must be 2 minus. That is soluble. And we've also got the 2 sodiums left over from the sodium hydroxide. You can put them together, but that's okay. We've done it this way this time. Doesn't matter. All right, let's write down some info that we know underneath. Okay, the acidity of the particular white wine was determined by titrating 25.0 ml of the wine. Okay, 25.0 ml of the tartaric acid. With, here we go, we've got a concentration of the sodium hydroxide, 0.0511 mole per litre. And it says to, when it reached the end point, it's 8.70 milliliters to the end point. Okay. All right. Don't like that red pen, I'm gonna swap. Okay, we can work out how many moles of the sodium hydroxide we had there at the end point. How much did it take to neutralize this acid? So, moles of sodium hydroxide at equivalence equals 0.0511 moles per litre. Multiply it to litres so it cancels. 0.00870 litres. Have we got that right? Yeah, 100 mil, 10 mil units. Cool. In our calculator, 0.0511. 0.0087, so I get 4.4457 times 10 to the negative 4 moles per litre. Moles per litre, 4 moles at equivalence. Okay, now that we know how many moles of this there was equivalence, we can work out how many moles of that there was at equivalence. So, moles of, was it tartaric? Yeah, tartaric. Tartaric acid equals the number of moles that we know of the other guy, 4.4457 times 10 to the negative 4 moles of sodium hydroxide, multiply it by the fraction between the moles. So sodium hydroxide will go on the bottom, so it cancels out. The tartaric will go on the top. What's the number in front there? 1. What's the number in front there? 2. So we're going to take the number of moles and multiply it by half, or divide it by 2. Okay, 2.22285 times 10 to the negative 4 moles. Okay, so at equivalence, there was this number of moles of the sodium hydroxide, so therefore there was half as many moles of the tartaric acid. Okay, so we worked out how many moles. What's the question asking us? Calculate the molarity of hydrogen ions in that wine. Okay, molarity, we're going to work out the concentration of the acid. So we need the volume, and it's given in the question, there was 25 ml. So let's work out the concentration of the tartaric acid. H2C4H4O6 is going to equal the moles, 2.22285 times 10 to the negative 4, divided by the volume in litres. 25 milliliters is 0.0250. Okay. Good go. 8.89. Oh, that's a terrible 8.14 times 10 to the negative 3 moles per litre. Okay, but the question is asking the concentration of H plus ions. Okay, let's do a formula to work that out. Calculate the molarity of hydrogen ions in the wine. Okay, we worked out the concentration of this, but we know it dissociates H2C4H4O6 goes to 2H pluses. They react with water. If you want to write it as hydronium, that's okay. Plus the conjugate base, C4H4O6, 2 minus. So that we know for every mole of this, we're getting 2 moles of that. So our concentration of H pluses, or H3O plus, the hydronium, 2 times 8.8914 times 10 to the negative 3 moles per litre. Put it in my calculator. Could probably do it quicker, but with my brain, not quicker. 1.77828 times 10 to the negative 2 mole per litre. Significant figures, because I'm reporting an answer. 3 in the volume, 3 in the concentration, 3 in the volume again. Let's do it to 3. Okay. 1, 7, 7 are your 3. First 3 significant figures. The fourth is 8, so this 7 needs to go up. 1.78 times 10 to the negative 2 moles per litre. 2, 3, sig, figs. That's terrible writing. There was still more to the question. It was very convoluted. Let's go. Okay. Assume that the hydrogen ions came entirely from diprotic tartaric acid and calculate the concentration of the tartaric acid in grams per 100 ml. Okay, we've got it here in moles per litre. We need to convert this into grams per, what was it? Grams per 100 milliliter. Okay, I'm going to do it over here. Okay, so if I've got something in moles per litre, oh, hang on, let me start again. If I want to get something in grams per 100 mil, set up my equation here, just with the units, and I've got moles per litre. Okay, we do it in a certain way, but I'm going to start this way. I'm going to multiply it by a fraction. I need to get rid of moles, so I'm going to put it on the bottom of this fraction. And I need to introduce grams up the top, so I'm going to put it on top. Okay? What's going to happen is the moles will cancel and I'll be left with grams per litre. That's not exactly what I want though, so I'm going to multiply it by another fraction. I don't want to get rid of grams, but I want to get rid of litres from the bottom, so I'm going to put it at the top. And I want 100 millilitres down the bottom. Okay? But notice that this is if I want this to equal 1, because I don't want to change the number, how many litres per 100 mil is 0.1. I've got to put a number in there so it equals 1. 0.1 litres equals 100 mil. So essentially this is just like saying multiply by 1. But it's telling me a path that I need to do. So it's saying, take the concentration in moles per litre, multiply it by grams per mole, or multiply it by the molar mass, and then multiply it by 0.1, okay? So we have 4.44, oh hang on, that's the wrong number. It's this one that I covered in a red box. 8.89, 14 times 10 to the negative 3 moles per litre, multiplied by the molar mass of tartaric acid. Oh, I didn't calculate that out, did I? That's okay. So we had 6 times 1.008 plus 4 times 12.01. Oh, so that's the hydrogens and carbons. What else have we got there? Oxygen. 6 times 16.00 grams per mole. And then, if you can see it in here, hopefully, I'm going to multiply it by 0.1. Okay, put it in my calculator. I still got that number? No. 8.8914 0.414 times 10 to the negative 3. I'm going to multiply it by the molar mass 6 times 1.008 plus 4 times 12.01 plus 6 times 16, and then I'm going to multiply it by the 0.1 factor at the end, and I get 0.133449 grams per 100 milliliters. 3 significant figures because of all the inputs before. 1 and the 3 and the 3 is significant. 4 is not, it's less than 5, so it's just 0.133 grams per 100 mil to 3 sig figs. All right, let's check how I did. 0.133 grams per 100 mil. Nailed it. Okay, we'll stop it there. Thank you.